Welcome you again. Welcome you all again in this talk on nowhere dense set. As I as in the previous talk, we have discussed about the separable sets, and before that talk we have seen the concept of dense set. So now we will consider, or I mentioned that sometimes we call it everywhere dense set. Okay. So I and everywhere dense set or simply dense set. But now today we will discuss nowhere dense set. So the first question is that the everywhere dense set is the opposite of nowhere dense set. So if a set is if a set A is not everywhere dense set, then it is nowhere dense set? No, it is not the case. Basically, there is no relation between everywhere dense set and nowhere dense set. Okay? Or you can say that there is no relation between dense set and nowhere dense set. But under what condition we can have some kind of the relations? We will see later. So a subset A of a metric space X is said to be nowhere dense set in X if the interior of the closure of A is empty set. Okay, that is, the closure of A contains no interior point. So the closure of A contains no interior point, or in other words, we can say that the interior of closure of A is the empty set. Then the set A is said to be a nowhere dense set. Now, let us consider some examples of nowhere dense sets. So, as usual, first we will consider a subset of a real line with the usual metric space. So, if we consider a finite set in the real line with the usual metric space, then we will see that it is nowhere dense set. And we see that the set of natural numbers and set of integers are nowhere dense set in R. Why? Because the closure of n set of natural numbers is equal to n, and the closure and the interior of n is equal to empty set, and therefore the closure of the interior of closure of n is equal to empty set, and therefore n set of all natural numbers is nowhere dense set in R. In the usual metric space R2, the set of all points on a line is nowhere dense set. Okay. In the discrete metric space, the empty set is the only nowhere dense set. Now, the notion of nowhere dense set, as I mentioned earlier, the notion of nowhere dense set is not the opposite of everywhere dense set. That is, if a set is not nowhere dense, then it does not imply that the set is everywhere dense. For example, consider the usual metric space R and the set A, okay, consisting the point X in R, where X lies between 0 and 1, in the open interval 0 and 1. Then we see that the closure of A, the interior of closure of A is equal to A, where A is not equal to empty set, and the interior of closure of the complement the complement of closure of A is the set of all points X, where X is less than 1 or X is greater than 1, which is equal to this open interval minus infinity to 1 union open interval 2 to infinity. Okay. So you can see that here is this set is A is nowhere dense set, okay, as well as not everywhere dense set. So here is we see that A is not nowhere dense set as well as not everywhere dense set. So we can see that the notion of nowhere dense set is not the opposite of the notion of everywhere dense set. Here I would like to give some remark. So first remark is that in a metric space, any subset of a nowhere dense set is nowhere dense set. You can prove it very easily. The closure of a nowhere dense set is nowhere dense set. Now, what about the interior? Whenever we are talking about the closure, we can also talk about the interior. Can you think about it? Okay. Just see, because you see here is the important thing, keep in mind the definition. We are already taking the interior, the closure interior, the interior of closure of A is equal to empty set. Okay. So if we have the closure of a nowhere dense set is a nowhere dense set. Now, can we have some characterization of nowhere dense set? Yes, we do have in the following form or in the following theorem. So, let X be a subset of a metric space X. Then A is nowhere dense in X if and only if the complement of closure of A is dense in X. Okay. A is nowhere dense set in X if and only if the complement of closure of A is dense in X. So, you can see that this result provides the relation between the nowhere dense set and dense set. Okay, so this is we can prove very easily. So, since the closure of complement of A is equal to the complement of interior of A, we have the interior of A is equal to the complement of closure of complement of A. Replacing A by closure of A, we get the interior of closure of A is equal to the complement of closure of complement of closure of A, and therefore the interior of closure of A is equal to empty if and only if X is equal to closure of X minus closure of A. So, we get the result. Now, corollary, let A be a closed subset of a metric space X. Then A is nowhere dense in X if and only if the complement of A is dense in X. So, here is again we can see that the set A is closed. So, if we are taking if A set is closed in X, then A is nowhere dense if and only if the complement is dense. So, you can see that here we have a little better relation between nowhere dense set and dense set, but we have to consider only the closed subset of a metric space. Now, for any subset A of a metric space X, we have the complement of the closure of A is the subset of closure complement of A, and therefore from this theorem it follows that if A is nowhere dense set in X, then the complement of A is dense in X. However, the converse is not true. For example, the set of all irrational numbers R minus Q is dense in the usual metric space R. However, Q is not nowhere dense set in R because the closure of Q is equal to R. Okay, this is all about the nowhere dense set. Now we come to another definition of a metric space which we call the first category. So, a subset A of a metric space X is said to be of first category if it is a countable union of nowhere dense set. Okay, so a subset A of a metric space X is said to be of first category if it is a countable union of nowhere dense sets. The set A is said to be of second category if it is not of first category. So here you can say is a subset A of a metric space is if it is not of first category, then it is of second category. First category means that if it is the countable union of nowhere dense set, or you can say that if it can be written as a countable union of nowhere dense sets. So here are some more remarks. Every subset of a metric space must be either of first category or of second category. So it is very, very important remark. We say that every subset of a metric space is either of first category or of the second category. It means that all the subsets of a metric space can be divided only in two categories, that is category of first category and second category. So if A and be a countable family of first category sets, then the union is of first category, because countable union of countable union sets is also countable. So if we have a countable family of first category, then their union is also of first category. If X is a metric space of second category and A1 is a subset of X is of first category, such that X is equal to A1 union A2. Okay, that is to say, if X is a metric space of second category, okay, and second category and A is a subset of X is of first category, such that the X is equal to A1 union A2, then A2 is of second category. A subset of a set of first category is of first category, because a subset of a nowhere dense set is a nowhere dense set. Now here we have two examples. The example number one is that empty set is of first category. The set of all rational numbers Q in R is of first category. Okay, so we can prove that in the following way, that if x1, x2, xn is an enumeration of the rational numbers, then each singleton set xi is closed and xi and the interior of this is equal to empty set, and therefore the whole set is therefore the union of xi is the set of all rational numbers in R is of the first category. So now finally I am going to present a very important result regarding the category or regarding the second category result. Okay, so that result says that it is known as the Baire category theorem. So I have put the photograph of Baire in the beginning of this chapter. Okay, and Baire was famous for his result, and that is known as Baire category theorem. So Baire category theorem says that every complete metric space is of second category. Every complete metric space is of second category. So again, I am going to recall you, I am going to mention you that a subset A of a metric space X is of first category if it is a countable union of nowhere dense set. So, a subset A of a metric space X is said to be of second category if it is not a countable union of nowhere dense set. So, second category means if it is not a countable union of nowhere dense set. It means that a second category space cannot be written as a countable union of nowhere dense set. So, here is we have the Baire category theorem. Baire category theorem says that every complete metric space is of second category. That is to say, every complete metric space cannot be written as a countable union of nowhere dense sets. So, let's prove this result. So, here is let An be a sequence of nowhere dense sets in a complete metric space X. Then we have to show that X cannot be written as the union of nowhere dense sets. Okay. So, X is not equal to this union. That is, there exists an element X in capital X such that X is not in An for all n. Okay, because we are taking the union, so A is not. Suppose that it can be written, X can be written as countable union of nowhere dense set. Since A is nowhere dense set, the closure of An, since each An is nowhere dense set, the closure of A has no interior point. So, any open sphere in X must intersect Gn, where Gn is equal to the complement of closure of An. So, because the closure of An is a closed set and the complement of this is your open set. So, Gn is your open set. So, it means that the closure of An has no interior point. So, any open sphere in X must intersect Gn for all n runs from 1 to infinity. Therefore, Gn is a family of dense open sets in X, and then by theorem this if Gn be a sequence of open dense sets in a complete metric space, then the intersection is also dense. So, here is and therefore, by this theorem, the intersection of this is non-empty. It follows that, so the intersection is non-empty, and it follows that the union cannot be equal to the whole space X, okay, which is a contradiction of our supposition, this one, okay, and therefore every complete metric space is of second category. Now, as a remark, since R is complete, by Baire category theorem, R cannot be written as a countable union of nowhere dense set. It's a very simple way. Corollary, if A is of first category subset of a complete metric space, then the complement of M is dense in X. So, if the corollary says that if M is of first category subset of a complete metric space XD, then the complement of M is dense in X. This very easily you can follow from the previous theorem. And second corollary says that a complete metric space is not a countable union of nowhere dense sets. And then, as I mentioned, again we have several exercises. Okay, so the first exercise is here. A is a non-empty subset of a metric space X, then prove that the following are equivalent. Or in other words, you can see that this exercise provides the equivalent definition of nowhere dense set. Okay, so if A is nowhere dense in X, it is equivalent to say that the closure of AA does not contain any non-empty open set. It is equivalent to say that every non-empty open set has a non-empty open subset disjoint from closure of A. It is equivalent to say that every non-empty open set contains a non-empty open set disjoint from A. It is equivalent to say that every non-empty open set contains an open sphere disjoint from A. So basically, from A to E, all these statements are equivalent. So in other words, you can say that these are equivalent definitions of a nowhere dense set. So you can prove it. And now here you have exercises. The Cantor set is nowhere dense set. The definition of the Cantor set is given in the appendix and you can see. Then here is if X is metric space, a closed set F is nowhere dense set if and only if it does not contain any open sphere. So here I have provided the solution. First you try to prove this exercise, to solve this exercise by yourself, and then if you could not succeed to prove this one, then you see the proof which is given over here. Now I also gave an exercise which says that if A is an open subset of a metric space X, then prove that A is dense in X if and only if the complement of A is a nowhere dense set. Remember, we have proved the similar result for the closed set. Then, as a result, you can use this exercise which says that prove that a finite union of nowhere dense sets is nowhere dense set. So this can be used as an result, but here I have put as an exercise. Again, you try to prove this one, that a finite union of nowhere dense set in a metric space is nowhere dense. Okay, if you could not succeed, then check the solution here. Okay, now we have several other exercises, but let us see here is I would like to mention that if XD is a metric space and A and B be non-empty subset of X, if the drive set A prime of A is nowhere dense, then A is nowhere dense set. If B is open, then the boundary set is nowhere dense set. And also you can prove very easily that the subset set of all irrational numbers of R is of second category. Okay. Finally, we have two more exercises which we say that prove that any non-empty open interval is of second category, and by using prove that use the Baire category theorem to show that the set of all irrational numbers Q is not the intersection of a countable union of open set. Also show that the set of all irrational numbers is not the union of a countable collection of closed sets. So this is all about the separability of a metric space. So here is in previous 4 talks we have discussed the first category, second category, dense set, separable set, first axiom space, 2 axiom space, and their characterizations, their results, and several exercises, examples. Okay, and we will move to the next topic, and the next topic we will discuss in the next talk. So thank you very much for your attention, and I hope that you will be enjoying my talks. Thank you very much.